Welcome to The Explainer. Today, we're jumping right into the physics of motion. How is it possible for a car to drive for miles and miles, but technically end up with zero velocity? And what is the real difference between taking that scenic, winding route versus a direct shortcut? Well, we're about to figure all of that out.
So let's start with a really basic question. We see things move all the time, right? But how do we talk about that movement with any kind of precision? What's the actual, measurable difference between taking a long, rambling road and a straight-line shortcut? The answer, it turns out, is all about how you measure the journey.
So here's the game plan for today. We're going to start with the absolute core idea of what motion even is. Then, we'll get into the nitty-gritty of distance versus displacement. After that, we'll throw time into the mix to look at speed versus velocity, and finally, we'll put it all together and see how it plays out in the real world.
First things first, what does it actually mean for something to be in motion? It sounds almost too simple to ask, but trust me, this definition is the bedrock for everything else we're going to talk about.
Okay, so the absolute key phrase here is relative to something else. Motion isn't some absolute thing. Think about it. If you're sitting on a train and another train on the next track zips past, it's obviously moving relative to you. It's always about how an object's position is changing compared to its surroundings.
All right, now that we've got a handle on what motion is, how do we actually measure the path something takes? This is where it starts to get really interesting, because there are two totally different ways to describe the same journey.
And here it is, the big difference. Distance is literally the total ground you cover, every single turn, every step. Just think of it as what your car's odometer tracks. Displacement, on the other hand, doesn't care about the path you took. It's just the straight line as the crow flies measurement from where you started to where you finished. It's the ultimate shortcut.
To make this totally clear, let's just follow a quick story about a student named Sham. He needs to get to school, but first, he's got to swing by his friend Ram's house to grab a notebook.
So let's add up the actual distance Sham walked. He went 7 kilometers to get to Ram's house and then another 8 kilometers to get to school. You add those up and you get a total distance of 15 kilometers. That's the entire path he actually took, every single step.
But what about his displacement? Well, if Sham could have just gone in a perfectly straight line from his house to school, that direct route would have only been 12 kilometers. See the difference? His distance was 15 kilometers, but his displacement was only 12. This is the perfect illustration of the winding road versus the straight shot.
Okay, let's add another layer to this. What happens when we bring time into the equation? Well, that gives us two brand new concepts that sound really similar but are actually worlds apart: speed and velocity.
This right here is the whole ballgame. Speed is simply how fast you're covering ground. It's just your distance divided by time. When your car's speedometer says 60 miles per hour, that's speed. Velocity, though, is all about displacement over time, which means it has to have a direction. So you wouldn't just say 60 miles per hour, you'd say 60 miles per hour north. That's velocity.
And hey, here's a quick pro tip for you. In our everyday lives, we talk about miles per hour or kilometers per hour, but in the world of physics, the official standard unit for both speed and velocity is meters per second. It's kind of like the universal language that makes sure all the calculations line up perfectly.
Just let that sink in for a second. Your car's odometer would clearly show that you traveled, right? You covered a real distance. But because you ended up right back where you began, your overall change in position, your displacement, is a big fat zero. And that one little idea is so important for getting the difference between speed and velocity.
So, let's take these ideas and apply them to a real journey. Because, let's be honest, motion isn't always nice and constant. Sometimes it's smooth, and other times, well, it's full of stops and starts. And that brings us to our final big concepts.
Uniform motion is just what it sounds like: steady, consistent, predictable. For every minute or hour that goes by, you cover the exact same amount of ground. That cruise control example is perfect. It's just smooth sailing at a constant speed in a straight line.
Now, non-uniform motion, this is what most of us deal with every day. It's the reality of driving in the city. You speed up when it's clear, you slow down for traffic, you stop at a light. The distance you cover minute by minute is always changing.
To really see this in action, let's look at some travel data from 3 different drivers. They all hit the road at the exact same time, but as you're about to see, their trips are very different.
Okay, here's the raw data. And at first glance, I know, it just looks like a bunch of numbers in a table. It shows the total distance each of them covered every half hour. But let's break this down because there's a real story hidden in these numbers.
First up, let's look at Amar. From 5 to 5:30, he drives 20 kilometers. From 5:30 to 6, he drives another 20. And from 6 to 6:30, you guessed it, another 20. In every single 30-minute block of time, he covers the exact same distance. This is the textbook definition of uniform motion.
Now let's check out Akbar. Whoa, his journey is totally different. In 1/2 hour, he covers 18 kilometers, but in the next one, he only manages 6, and then he floors it and covers 28. His distance is all over the place. That, my friends, is classic non-uniform motion.
Okay, so now it's your turn. Take another look at that table and check out Anthony's journey. Is he covering equal distances in each half-hour block? Go on, take a second and think about it. Is his motion uniform or non-uniform?
And really, that's what it all boils down to. These aren't just a bunch of random vocabulary words to memorize. They're tools. By really understanding the difference between distance and displacement, and speed and velocity, we get this incredibly precise language to describe and analyze how literally everything moves in the world around us.
So let's end with a little brain teaser. Remember that race car that drove in a perfect circle? Its odometer proves it was moving. It definitely had a speed. But since it ended up exactly where it started, its displacement was 0. So, what does that mean for its average velocity over that lap? Think back to the formula. Thanks for watching.